Welcome back. In this video, we're going to talk about how to select a bearing at a different reliability than the manufacturer's provided reliability. Recall when we talked about bearings, we talked about how they fail stochastically, which means we don't necessarily know when a particular bearing is going to fail. Instead, we have a prediction based on the probability of a failure occurring in that lot. So what we have is a number of failures for that type of bearing over time. So recall that our ratings of C10 and L10 are such that at a load of C10, the life that we can expect where 90% of the bearings will still be working at that load of C10 is our L10 cycles. And so a manufacturer will specify their reliability. So they may pick 95% reliability, they may pick 90. They will specify the rating lifetime, so how many cycles they refer to. So we have two examples in our textbook, one with 1 million cycles and one with 90 million cycles as the base. And they will also specify the shape of the reliability curve. All right, and that's fine, and that allows us to pick a bearing based on our approach to finding the catalog rating. So the catalog rating is whatever application factor is appropriate for our particular application, depending on the shock loads and things like that, multiplied times the force, the reaction force that our bearing has to withstand, and then the life that we want to get out of the thing. So our life desired divided by our rated life raised to the 1 over A, where again A equals 3 for ball bearings and A equals 10 over 3 for roller bearings. All right, so that gets us a bearing at the reliability that our manufacturer has specified. So for example, it may be 90%. But what if that's not good enough? So consider, for example, you've got generally 2 bearings on a shaft. So here's our gear, and then the other shaft. The probability that this thing failing is the probability that one of the bearings fails. So that means, so the probability of success is 1 minus the probability that both of them succeed. So that is, if one bearing fails, the whole shaft fails. So in order for them, how we represent that is the multiplication of them. So the reliability total is the multiplication of the reliabilities of each one on the same shaft or within the same system. So if they are independent reliabilities or independent probabilities of failure, which these are, so if one bearing fails, the behavior of one bearing doesn't have any effect on the probability of the other bearing failing. So if their probabilities of failure are independent, then we can multiply their probabilities of failure, or alternatively 1 minus that, and that's your reliability, and come up with a total reliability. That means that if we pick a 90% reliability of bearing 1 and multiply it times the 90% reliability of bearing 2, we actually end up with a smaller system reliability of only 0.81. Now that may be below what we're willing to accept in terms of risk, but that's a design decision. You have to decide for your application what you're willing to risk. So if we're not willing to risk that, that means we need to select a higher reliability. So in terms of our Weibull distribution, what this says is we have one distribution that looks like this, and we have an L10 based on a C10, and what we want to do is figure out where we would need to pick a different C10 and move from one Weibull curve to another. So the way to do that is we're simply going to modify our catalog equation to move from one reliability curve to another. So if we want 90% reliability, just use the one we have. But if you want a higher reliability, what we're going to need to do is modify it such that now we're going to look for a catalog a rating of the same application factor, the same load that our bearing needs to resist, but now we're going to have to modify our expected life ratio according to the reliability curve we want to be on. So using a Weibull distribution, we will have the formulation that looks like this. So these values, x naught, theta, and b, are the shape parameters of the Weibull distribution. X naught is the mean that the shape is based around. Theta and b, or beta, depending on your representation, basically change the shape, the width, the height of these Weibull distributions. So these will be specified by the manufacturer. And it's basically a line fit based on their experimental findings. And again, 1 over A is the same thing with the ball bearings or roller bearings, depending. So what are these parameters? Well, XD, that is our point that we care about, our L10 versus our LD that we are actually at. So the life that we want to get out of this thing in terms of cycles divided by the rated life is the point with which we start. So if you wanted 90% reliability, basically this equation down here is going to turn to 1, or very close to 1, and you'll get exactly the same thing as you had before. But if you want a higher reliability, so if your reliability desired is greater than 0.9, or whatever reliability the manufacturer is based on, most of them are 90%, some are higher for precision bearings. If you want a higher reliability, then you can use this equation for the catalog rating and get there. So there's two formulations. One has a 1 minus the reliability that you want, raised to the 1 over b in there, multiplied times the other stuff. And one has the natural log of 1 over the reliability you want, all of that raised to the 1 over b. These two are effectively equivalent. It's a small number approximation to use the 1 minus RD. It's a little bit simpler and doesn't require you to use a natural log. Obviously, we've been picking bearings for a while, and we haven't always had calculators that easily calculate different natural logs. So 1 over RD is a simplified approximation. You can use either one. You'll come up with very similar values, and the error is going to be very small. So we'll simply do this, and it will push us to be picking a higher reliability, a higher catalog rating than we would have if we simply ignored this Weibull distribution and picked it based on our life ratio that we want to be at. So let's see how that works So the book lists two different manufacturers, and manufacturer 1 uses a baseline L10 of 90 times 10 to the 6 cycles. And the Weibull parameters, x naught of 0, a theta of 4.48, and a b value of 1.5. If we have two bearings on a shaft and we want to receive a total reliability of, say, 0.90, we could do that in a couple different ways. So any two numbers that multiply together to get 0.99 or 0.90 would get us that value. and we would have to decide what we want our reliability to be. So if one is under a higher load, it makes sense to reduce the reliability requirements of that one and up the one that has a smaller load, because that will allow us to pick fine bearings that will work. So for example, we could pick, if we need a reliability of 0.90, and one of these bearings will be very hard to find a bearing for because it's got high loads, we could find a reliability maybe 0.099, and that requires that our other reliability be 0.99. So we'll have to, let's examine and try to find a bearing at this higher reliability. So for example, the reliability we want is 0.99. The load, the radial load that our bearing is going to have to handle is, let's call it 12 kilonewtons total. So that is, the bearing has two reaction forces, and FD was the square root of perhaps the direction in the y direction squared plus the force in the z direction squared, and we found the radial reaction. For this example, we won't use any axial force. We'll save that for the next video. So altogether that gave us 12 kilonewtons, and an application factor for this particular load is 1.2. Different application factors depend on the type of loading you'll be under, and you can look at the tables to find around approximately a appropriate application factor. All right, so let's choose a ball bearing that will spin at 300 revolutions a minute. It will last 90,000 hours, and it will be a deep groove ball bearing. That tells us where in the table we need to look, right? So first off, we need to figure out what is our baseline life ratio that we need to find. So it spins at 300 revolutions per minute for 90,000 hours, and there are 60 minutes in an hour, all over its baseline rating. And so we said for manufacturer 1, we're going to use 90 times 10 to the 6 as our baseline rated life. So altogether, that equals 18. All right, so that's our baseline if we wanted 90% reliability. If we want 99% reliability, we need to use the Weibull parameters and find the specific one that we're interested in. So our C10, again, equals application factor, dynamic force, the baseline life, and then the Weibull parameters, x naught plus theta minus x naught multiplied times, and well, let's use the ln one here, the natural log of 1 over our reliability desired, raised to the 1 over b, and this to the 1 over a. So for our particular situation, this looks like C10 equals 1.2, our application factor, multiplied times our dynamic load of 12 kilonewtons. So recall, our ratings are going to be in kilonewtons, so we can just use 12 here for our forces. And again, the units of this will be kilonewtons, multiplied times 18, divided by all of our Weibull parameters. So x naught is 0, so we just have the theta value, 4.48, multiplied times the ln of 1 over 0.99, the reliability we wanted to get, raised to the 1 over 1.5, that's the beta parameter, and all of that raised over to 1 over 3. And again, we're using ball bearings, so A will be 3 in this situation. All right, plugging all those values in, we find a minimum catalog rating that we need to find of 63.6 kilonewtons. So let's see if we can find a deep groove ball bearing in our catalog that will allow us to do that. So we can look for our deep groove ball bearings, not our angular contact. We'll use angular contact when we're dealing with thrust loads. So we won't look at those right now, but we'll look at deep groove ball bearings. This is the 02 series in the textbook. And we need to find a rating that will handle 63.6 kilonewtons. So 61 is not quite enough. What instead we want is the 66.3 kilonewtons. That requires that we have a bore of 75 millimeters. So to specify this bearing, at 99% reliability, we need a 02 ball bearing, deep groove ball bearing with the 75 millimeter bore diameter. So that's an example of how we find a ball bearing using a particular reliability higher than the catalog rating. Now, you can use the exact same process and look for roller bearings. You just need to use the appropriate roller bearing catalog table instead of this ball bearing catalog. All right, that'll about do it for this video. Until next time.